Welcome everyone. Today we have a talk by Heinrich Wansing, a professor of logic and epistemology at the University of Bochum. Heinrich is well known for his work on the semantics and proof theory of different non-classical logics. And today he's going to speak on so-called connexive logics. Thank you, Heinrich, for accepting the invitation. Please.
Yes, thank you very much, Stanislav, for inviting me to this St. Petersburg logic seminar with participants not only from and in St. Petersburg. So it's a great pleasure. And it's good to see you all, and thank you for participating. You already mentioned that this talk is based on a paper that will also be presented at this year's Advances in Modal Logic conference. And so it is joint work with Hitoshi Omori, and I'm very happy that Hitoshi is also participating. So thanks a lot, Hitoshi, because it's very late at night at Kamakura in Japan already. Yes, so it's the first time that I will present this paper. I hope that I will not run too much out of time, but we will see. Okay. So as you already said, and as you see from the title, this is a talk about connexive logic. And connexive logic is an area that is still not very well known. And I hope that I can convince you by this talk that it is an interesting area and worth of investigating and maybe also worth of applying. Okay. So what is now? Oh yes, sorry. So what is connexive logic? So connexive logic is normally characterized, connexive logics are normally characterized as systems that validate certain theses, which are named after some famous philosophers, namely Aristotle and Boethius. So they are Aristotle's thesis saying that it's not the case that not A implies A, and it's not the case that A implies not A. So no formula implies its own negation is the idea. And there are Boethius' thesis saying that if A implies B, then it's not the case that A implies not B, and if A implies not B, it's not the case that A implies B. Usually it's also required that A implies B implies A is not a theorem, so as to prevent an understanding of the connexive error, connexive implication as a biconditional. Now, these theses seem to be endorsed by quite a few natural language speakers from different cultures. So if there's some empirical work to the effect that people find these principles plausible, if they have not been brainwashed by a course in classical logic, of course. Now, these theses are not valid in classical logic. And this means that connexive logics belong to a larger family of non-classical logics known as contra-classical logics. So they are orthogonal to classical logic, and it means that due to the post-completeness of classical logic, we have to give up some classically valid principles in order to avoid triviality. Now, in a certain paper I wrote a while ago, I suggested to capture these connexive theses by means of a suitable falsity condition for the implication, and by building on the very well-known four-valued paraconsistent logic known as first-degree entailment logic or Bell-Dunn logic. So in particular, I defined a system of connexive logic called C for connexive, and I introduced it as a variant of David Nelson's paraconsistent constructive logic N4, which basically extends first-degree entailment logic by intersynergistic implication. Now, some people think that this is a very simple and natural connexive logic, and this is maybe important because in the literature you can find quite a lot of non-simple, very complex and not so natural connexive logics. And in this talk, I will consider an extension of C that is obtained by adding the law of excluded middle, LEM, with respect to the strong negation. So the negation of this connexive logic C, the negation from FDE, is sometimes referred to as strong negation because it expresses definite falsity. It's a strong kind of saying no. And so how is this consideration of adding the law of excluded middle to this connexive logic C, which you have not yet seen, how is it motivated? Now, it's motivated by three questions. So this is a picture of John Cantwell in Stockholm. And in a paper from 2008, he tackled the question of how to negate indicative conditionals in natural languages. And there he defends these three-value truth tables, which one can already find in work by Newell Belknap on conditional assertion. So CN stands for conditional negation. And here's the third truth value, the dash. And this value is meant to be a Geppy value. And when a conditional has a false antecedent, it has this dash value. It lacks the truth value. Now, as a result, two formulas, not A implies B and A implies not B, then receive exactly the same value for every assignment. So they are equivalent. And this already expresses the understanding of false conditionals. I mean, the negation of A implies B is understood as A implies not B, and not as in classical logic as A and not B. And then Cantwell defined the consequence relation by designating both the value T and this Geppy value. So the idea is to preserve non-false values in entailment. And as a consequence, his logic includes both Aristotle's and Boethius' theses. Thus, the logic is connexive, although he does not mention connexive logic in his paper at all. So he was not aware of this research tradition. Now, this logic of conditional negation, it has the feature that its implicational fragment is classical. So it uses Boolean implication. And this means that formulas such as A implies B or B implies C hold for arbitrary A, B, and C. So there are attempts at making sense of the material conditional as an indicative conditional. So there are some papers in the literature that defend indeed Boolean implication as representing the indicative conditional in natural language. But it also seems very natural to wonder whether one can replace the classical conditional by a better conditional, such as the constructive conditional. So and this already gives us the first question that motivates the paper, namely to explore an extension of the connexive logic C by the law of excluded middle, which will give such a combination of a constructive implication and the law of excluded middle. There's a second question that motivates our paper. So these are Luis Estrada Gonzalez and Eli Ramirez Camara, and they wrote a paper where they offer a list of desiderata for connexive logics. And the question we ask is how many desiderata can be met by connexive logics that follow this idea of tweaking the falsity conditions of the conditional, so as to obtain the connexive principles. And their list of desiderata contains more than the two characteristic pairs of these connexive principles. In particular, they also list what is called Aristotle's second thesis and Abelard's thesis in the literature. So Aristotle's second thesis says it's not the case that A implies B and not A implies B. And Abelard's thesis says it's not the case that A implies B and A implies not B. Well, what should we think about of these additional principles discussed in connexive logic? Well, on the one hand, in a paper with Daniel Skurt, I argued that these theses should not be considered as characteristic of connexive logics because they are motivated by the idea of negation as cancellation. And we believe that this is not a good idea. But to be fair, the above formulas, Aristotle's second thesis and Abelard's thesis, they are included also in probabilistic approaches to conditionals. And it seems that interest into these formulas goes beyond technical curiosity. So they seem to capture some intuitions on conditionals. Be this as it may, the system C, which you will see in a moment, it fails to include Aristotle's second thesis and Abelard's thesis. But this does not mean that variants of C will also both fail both theses, or at least one of these principles. And this is our second question, namely, well, to look whether by extending C we can capture more theses in the spirit of connexive logic. And there's a third question. It is somewhat related to the first, and the question is, what is the relation between constructivity or constructiveness and the law of excluded middle? And I hope that this question is of a slightly broader interest. So, I mean, I said connexive logics are not so terribly well known. They are sort of unusual. But this question about the relationship between constructiveness, constructivity, and the law of excluded middle, it is maybe of more general interest to people interested in proof theory. So here's a quote from a paper by Jeremy Abigat. He says, the words constructive and intuitionistic are used today almost interchangeably, and I think he's not the first and only person who has made such a statement. There's another quote from Yves Lafont in this book with Proofs and Types with Jean-Yves Girard as the main author. And Lafont says, intuitionistic logic is called constructive because of the correspondence between proofs and algorithms. Well, then intuitionistic implication indeed is essential for reading intuitionistic logic as constructive logic. So if we want to have this correspondence, then yeah, we better use the intuitionistic implication. And according to Paul Gilmore in a paper from 2005, the disjunction property and the existence property together are, quote, the hallmark property of an intuitionistic constructive logic. I think Michael Rathjen has made some similar statements. As some of you may know, this conception of constructivity has been challenged by David Nelson, who said that, well, this is not enough. So in addition to keeping the intuitionistic implication and having the disjunction and the existence properties, he also wanted to have the dual of the disjunction and the existence property. So the constructible falsity property, which says that if the negation of A and B is provable, then the negation of A is provable, or the negation of B is provable. And the dual of the existence property, which says that if the negation of for all x ax is provable, then the negation of A of t is provable for some term t. Good. Now, the third question does not make sense if we consider intuitionistic logic, if this is our starting point. Because if we add the law of excluded middle, as you all will know, what we obtain is classical logic, and this is admittedly non-constructive. If we add the law of excluded middle to Nelson's three-valued constructive logic, then again we will have a collapse into classical logic. The situation is different if we add the law of excluded middle to Nelson's four-valued logic. This will not give us classical logic, but a logic that is known in the literature as Clance. It's a three-valued logic that is obtained by expanding the logic of paradox, this well-known three-valued part-consistent logic due to Arsenian Priest, by the following truth table. Okay, but the negation-free fragment of Clance is classical. Thus, if we add the law of excluded middle, it would destroy the constructive features, including the intuitionistic implication, the disjunction property, and the existence property. But the proof of this collapse of Nelson's four-valued logic into Clance, it heavily relies on the falsity condition for the conditional. And this is just exactly what we want to change, what we change if we go from Nelson's four-valued logic to its connexive variant C. So this motivates our third question to look at the effect of adding the law of excluded middle to C, which has this non-standard falsity condition, different from the classical falsity condition we have in Nelson's four-valued logic. And we will see that the addition of the law of excluded middle to a logic with constructive implication need not collapse into classical logic. Moreover, the addition of the law of excluded middle for atomic formulas need not prevent the existence properties and its dual from holding. And this is, I think, quite a nice observation. So here's the structure of the talk. Finally, I will revisit the connexive logic C. So maybe at this point you are eager to see what it is. And then in the next step, I will introduce its extension by the law of excluded middle. Then I will discuss the first two questions at the level of propositional logic. And finally, I will introduce the extension of quantified C obtained that we get if we add the law of excluded middle. And we discuss the proof theory of this quantified version of C and its extension by the law of excluded middle and the law of excluded middle for atomic formulas. Okay, so at the moment we are at the propositional level. So the language consists of these connectives, the strong negation, conjunction, disjunction, and constructive implication. And we use some standard notation. So P and Q are propositional variables. A, B, C stand for L formulas, and uppercase Greek letters delta, gamma, sigma stand for sets of L formulas. And here's the semantics. So a C model for this language is a triple consisting of a non-empty set of states and partial order on that set. So we're taking an intersymbolic Kripke frame, and then we add a four-valued valuation function. So it's an assignment of truth values to state variable pairs, and we have two persistence or heredity conditions. So, and then such a assignment function is extended to an interpretation according to the clauses listed here. So we have these four values. The empty set intuitively means neither true nor false. The singleton set 0 means true and only false and only false. The singleton set containing the classical value 1 means true and only true, and this means both true and false. And if we look at these clauses, then the clauses for the negation are such that they give you the double negation laws. So 1 belongs to the interpretation of not A at state W, if and only if 0 belongs to the interpretation of A at W, which means W supports the truth of not A if W supports the falsity of A. And the clauses for conjunction and disjunction are such that they give you the De Morgan laws. So we have the semantics for first degree entailment. And what is interesting then are the clauses for implication. So W support the truth of A implies B, meaning 1 belongs to the interpretation of A implies B at W. If for every state W1 above W, we have that at W1, the truth of A is supported. So this is just the intuitionistic understanding of implication. And what does it mean that state W supports the falsity of A implies B? Well, 0 belongs to the interpretation of A implies B at W. If for every state W1 above W, every information state that expands the state W, if W1 supports the truth of A, it supports the falsity of B. So here you see this idea that the falsity of A implies B means A implies the falsity of B. A implies not B, but intuitionistically. So this holds for all extensions of the state of evaluation W. Good. So this is a very, very clear and transparent semantics, and it gives you a connexive logic. And this is quite different, as I already mentioned, from other systems of connexive logic, which sometimes have a very, very complicated semantics. Now then, semantic consequence is defined as in a very traditional way. So gamma entails A, the set of formula gamma entails A in logic C, if for every model and every state from that model, if that state supports the truth of every premise, it supports the truth of the conclusion A. And the only difference indeed to the semantics for Nelson's logic N4 is with respect to the falsity condition for implication. So in Nelson's logic N4, a state W supports the falsity of A implies B if W supports the truth of A and the falsity of B. So this is falsification on the spot, whereas the falsification of implications in C is dynamic. It's not falsification on the spot. There's an axiomatization of this semantically defined logic, and it's also very transparent. So if you look at the axioms A1 to axiom 1 to 8, These are just the axioms of positive intuitionistic propositional logic. And what we then add are the double negation axioms. So the axiom of double negation, introduction, elimination. These equivalences that give you all the axioms 10 and 11 that give you all the De Morgan laws. And the characteristic axiom for negated implications. So not A implies B is equivalent to A implies not B. And then we have modus ponens. So this is also a very simple and transparent axiom system. And you can really see what is going on here. Yes. So you take an axiomatization of N4 and replace the axiom for negation implications by this connexive reading of negation implications. We can define the notion of derivability in this axiom system in the standard way. And as I already said, if we replace this contra-classical connexive axiom 12 by this one, we obtain an axiomatization of N4. And we have a characterization of this axiom system by the class of all C models. So we have strong completeness result. Good. No, first of all, we have the characterization, but first of all, which comes as no surprise, we have the deduction theorem. But we also have this strong completeness. Now we have a highly unusual property of C. C is contradictory logic. It is negation inconsistent. This is very, very unusual. You know from paraconsistent logics that they are inconsistency tolerant. You cannot derive whatever from contradictory premises. But here we have provable contradictions. So here's an example. A and not A implies A is provable in C. This is because we have simplification. Yes, from A and B implies A and B implies B. So A and not A implies A. But we can also derive the negation of A and not A implies A. Well, this negated implication is equivalent to A and not A implies not A, which is derivable and provable because we have simplification. Okay. It's interesting that the proof of inconsistency relies on very weak assumptions. So even if we use a very weak relevant implication or a very weak conditional with the semantics as it is used in conditional logic, we still have this inconsistency. And this may prompt a question. So is the axiom 12, not A implies B is equivalent to A implies not B, is this axiom or the falsity condition for implication from C, this non-standard falsity condition, is this responsible for the inconsistency? Will this always give rise to inconsistency of the system? And the answer is no. And this is an observation by Hitoshi Omori. So there's a consistent axiom, a consistent system with the axiom 12, not A implies B equivalent A implies not B. And the proof is not so simple, not so difficult. So take the propositional logic where we now have just negation and implication, of course. And then consider an axiomatic proof system with axiom 9, the double negation axiom, and this connexive axiom 12, and modus ponens. And for any axioms for implication, you have an even number of occurrences of variables. Then one can see that such a proof system is consistent. One can take the two-valued matrix for classical logic, interpret the negation as classical negation, and the implication as the Boolean bi-implication. So this is interesting. So we have this non-standard, contra-classical, connexive axiom expressing the connexive understanding of the falsity conditions for implications, but this is not necessarily something which would give rise to an inconsistent contradictory logic. We finally come to the main extension of C. So in the semantics, what do? We just close the gap. So instead of considering 4 valid assignments, we consider 3 valid assignments. So we remove the empty set from the range of the evaluation function. And we still require persistence. So I think I did not explicitly mention this when I introduced the C models. So the idea is if a state W1 supports the truth of an atomic formulas and you go to an extension of that state W2, then still support the truth of that atom, and similarly for support of falsity. Good. And with this change of the semantics, with this closing of the gap, we still have persistence for arbitrary formulas. And we can define an axiomatic proof system for this semantics, for this semantically defined logic C3, by just adding the law of excluded middle. Good. And then we can define derivability in this extended logic as usual. And we have soundness of this extended axiomatic system, and completeness can also be proved in a standard way. So we define the notion of deductively closed sets and prime deductively closed sets. And of course, a set of formulas is non-trivial if it is distinct from the set of all formulas. Then we have this Lindenbaum lemma. So if A is not derivable from sigma in this axiom system C3, there's a non-trivial prime deductively closed set extending sigma such that delta also does not allow to derive A. For the completeness proof, we make use of this lemma. If sigma is a prime deductively closed set and A implies B does not belong to sigma, there's a non-trivial prime deductively closed set theta that extends sigma such that A belongs to theta and B does not. And then it's in quite standard way we can prove also the completeness theorem. Good. Now let me come finally to the questions we raised. So the first question concerned this system by John Cantwell. We asked if we can replace the classical conditional, the Boolean implication, by a constructive conditional. Now, from a semantic point of view, it's easy to see that C3 expands positive intuitionistic logic conservatively. But we have the following observation due to Hitoshi Omori that justifies to claim that C3 is a generalization of Cantwell's logic. So the extension of C3 by Peirce's law is sound and complete with respect to the semantics induced by the following matrix, with T and B as designated values. But then we can see that this extension is the system Cn of Cantwell. So C3 extended by Peirce's law gives you Cn. So we can add Peirce's law to a logic where we have the intuitionistic implication. And actually, Grigory Orkovikov, independently of John Cantwell, you also introduced and discusses the above three-value truth table. What happens if we add Peirce's law to C? If we add Peirce's law to C, this gives one a four-weighted logic, which is sometimes called material connexive logic, MC. And it is induced by the matrix that we get by adding the following truth table for the conditional to the truth tables for FDE. And an expansion of this logic by Boolean complement has been explored in a paper by Hitoshi. What is perhaps also interesting is that in view of these results, we can consider intermediate logics between C3 and Cantwell's logic, as well as between C and this material connexive logic. And this is maybe an interesting problem. Now we come to the second question. How much connexivity can be captured through the present approach via tweaking the falsity condition? So we build on the list of desiderata presented by Estrada Gonzalez and Ramirez Camara, which includes these four connexive principles, say. And we can first observe that the systems C and C3 are not able to capture all of the above four theses. Aristotle-Boethius thesis, the theses that are characteristic of connexive logic, they are derivable in C and C3. Well, they are derivable in C and hence also in C3. But C fails to include Aristotle's second thesis and Abélard's thesis. But C3 includes Abélard's thesis, but not Aristotle's second thesis. So, if we go from C to C3, we are able to capture one more thesis, which has been discussed in the literature about connexive logic. So we are a bit more flexible. However, as Aristotle's second thesis still is not captured. But this is not the end of the story. We may consider another implication, namely the defined so-called strong implication. So we define A double arrow B as A implies B and not B implies not A. So for this strong implication, we have the contraposition rule, but we also have another interesting result, namely all four theses listed above are derivable in C3 with respect to the strong conditional, the definable strong conditional. Only Aristotle's and Boethius theses formulated in terms of the strong conditional are derivable in C. So C is quite reluctant when it comes to Aristotle's second thesis and Abelard's thesis. And this has also been observed by Hitoshi. Good. So we may note that all four principles formulated in terms of the strong implication hold in Cantwell's logic and also in this system of material connexive logic. This is so because the negation of A strongly implies B is equivalent to not A implies not B or not B implies A, that it is equivalent to an instance of the linearity axiom, which means that for arbitrary formulas A and B, we have the negation of A strongly implies B is valid. This is certainly not wanted. Okay. But fortunately, this is in sharp contrast with what we have in C, because there it's not the case that the negation of A strongly implies B is valid. Good. So we can summarize our observations so far in the table. In the table. So here we have the four logics and the two implications, the weak one and the strong one. And you can see that C3, Cantwell's logic of conditional negation and the material connexive logic, they all have ticks here. So they all validate the four principles, but unfortunately MC and CN also have a tick here. So they have this unwanted property that every negated strong conditional is valid. So we may say that the contraposable strong negation of C3 seems to be quite interesting. It satisfies all contraclassical theses considered by Estrada, Gonzalez, and his co-author, without having the problematic looking formula as a valid formula. Good. But again, this is not the end of the story. So Estrada, Gonzalez, and Ramirez Camara, they consider a bigger list of desiderata. And so they want that the positive paradox of implication is not valid. They want that the negative paradox of implication is not valid. They want that they want to avoid the paradox of necessity. They want to have simplification, which I think is good. Yes, they want to have idempotence. A and not A implies A, and A implies A and not A. And what is of interest in what follows is that they also want the logic to be Kapsner strong. So you will remember Aristotle's thesis. It's not the case that A implies not A. So this should be valid in a connexive logic. But Andreas Kapsner, he also, in addition, postulates that A implies not A should be unsatisfiable, and also that A implies B and A implies not B are not simultaneously satisfiable. So when all these desiderata are satisfied, Estrada, Gonzalez, and Ramirez Camara speak of totally connexive logics. And they leave it as an open problem whether there exist totally connexive logics, and if so, which one is the minimal. Good. So, in view of what we have seen, there are three candidates for totally connexive logics, where we had all these the four ticks at the four connexive principles: C, MC, and Cn. If we look at the contraposal conditional, because for the weak one we will not get all the four principles. Now, since both C3 and MC are subsystems of Cm, and since the list of desiderata involves invalid invalidities, it makes sense to focus on Cantwell's Cn. And then the truth table for strong implication in Cn is this one. Okay. But then Hitoshi Yomori noticed that this truth table is not new. It was already introduced and discussed by Chris Mortensen in a logic that was later called N3V. And we can recall that this is an expansion of the logic of paradox obtained by adding the above conditional, this one. Now, it turns out that Cn and M3V are equivalent systems. This is again an observation by Hitoshi. And so one direction is not so difficult, but we also have to show that the non-contraposal conditional of Cantwell's logic is definable in M3V. And this can be verified by checking that this formula defines the weak implication. Good. Okay. Now, Estrada Gonzalez and Ramirez Camara consider M3V, and it is shown to satisfy all the desiderata except Kapsner strength. But maybe we can obtain a logic that is Kapsner strong. Well, we may conclude that all three candidates enjoy the same status, because we have simplification and idempotence also for C and hence for C3. Can we come up with the property of Kapsner strength, or can we, yes, somehow redefine this, or can we be a bit more sophisticated? Now, in the vicinity of first-degree entailment logic, there are always two ways to formalize classical notions, because truth and non-falsity come apart. Yes, and falsity and non-truth come apart. So this means if we look at satisfiability, we can draw a distinction between positive and negative satisfiability. So for this three-valued logic M3V or Cn, we may say that the formula A is positively satisfiable if there is a valuation such that 1 belongs to the interpretation of A. And A is negatively satisfiable if there is an M3V valuation such that 0 does not belong to the interpretation of A. So we have a more subtle conception of satisfiability. We draw a distinction between positive and negative satisfiability. So it was observed that M3V is not Kapsner strong if satisfiability is understood as positive satisfiability. But it is indeed Kapsner strong if satisfiability is understood as negative satisfiability, since 0 belongs to the interpretation of A strongly implies B for all valuations V and all formulas A and B. So we can now define the notions of positive and negative satisfiability for C3 and C3 models. Yes. A is positively satisfiability if there is a C3 model and a state from that model such that the state supports the truth of A. And A is negatively satisfiable if for some C3 model and state from that model, the state fails to falsify A, fails to support the falsity of A. Then C3 is Kapsner strong if satisfiability is understood as negative satisfiability. So what can we say? There exist totally connexive logics, including C3, MC, and Cn, if we look at the contraposable conditional, and if we think of satisfiability as negative satisfiability. So C3 enjoys the additional feature of being totally connexive without all negated conditionals being valid. And here's a summary of a table that summarizes what we have said or seen about the relationships between extensions of C so far. So on the left-hand side, we see that if we add Peirce's law to C, we obtain this material connexive logic. If we then add the law of excluded middle again, we obtain Cantwell's logic, or this M3V, three-valid logic. If we add the law of excluded middle to C, we obtain our logic C3, C plus the law of excluded middle. And the situation is slightly different if we look at N4. Here, if we add Peirce's law, we obtain a logic that is sometimes called HBE. And the addition of the law of excluded middle to N4 and this HBE gives us this already mentioned logic clans. Good. Now we come to first order logic and to these proof theoretically more interesting questions, maybe. We consider the expansion of C and C3 to quantified versions, Q, quantified C, and quantified C3 in a simple language, in a simple first order language without function symbols and equality. So we add individual variables, individual constants, predicate symbols of finite arity. There's an axiom system for quantified C, it is also quite transparent. We add axioms that allow the interdefinability of the existential and the universal quantifier by means of strong negation. Good. And then we have these two axioms and these two rules, which are quite standard. So we have universal instantiation and existential generalization. To this axiom system, we can add either the law of excluded middle, LEM, or the law of excluded middle for atoms, so P or not P for atomic formulas P. We can then define deducibility in these axiom systems in the standard way. And the axiomatic system quantified C, it is shown to be complete with respect to suitable cryptic semantics with increasing domains by applying a certain proof method, namely by a faithful embedding into positive first-order intersynergistic logic. Unfortunately, this proof method is not obviously available to us. Why? Because it's not clear into which system we can embed quantified C3. For that reason, we leave this as an open problem at the moment, and we consider proof-theoretic aspects of quantified C3. And quantified C3 add, where instead of the law of excluded middle, we add the law of excluded middle for atomic formulas. And what will we do? We define cut-free sequence calculi for these logic. The presentation is based on a certain paragraph in Sarah Negri and Jan von Plato's book about structural proof theory, where this sequence calculus G3 for intersynergistic predicate logic, so the G3 sequence calculus for intersynergistic predicate logic, is extended by a rule that captures the law of excluded middle for atomic formulas. Good. So if we add this sequence rule that captures the law of excluded middle for atomic formulas to the sequence calculus for intersynergistic propositional logic, the G3 sequence calculus for intersynergistic propositional logic, what we get is a sequence system for classical logic. If we add this rule to the G3 sequence calculus for intersynergistic predicate logic, what we obtain is a proof system for an extension of classical logic, extension of classical propositional logic by the intersynergistic universal and particular quantifiers. So they are not interdefinable by means of negation. Now, Negri and von Plato remark that the proof of admissibility of excluded middle for arbitrary formulas for this G3 sequence calculus for intersynergistic propositional logic plus the atomic law of excluded middle rule cannot be extended to quantified formulas. Therefore, we add an excluded middle rule for arbitrary formulas to the sequence calculus for C, for G3 sequence calculus for quantified C. And for the addition of the atomic law of excluded middle rule to the G3 sequence calculus for C, we prove the existence property and the dual existence property. So we have the law of excluded middle for atomic formulas, which means that we do not have the disjunction property, but we nevertheless will have the existence property. This is the interesting thing at this point. So we use uppercase Greek letters for finite possibly multisets, and the double arrow now is the sequence arrow, or not the strong implication anymore. So we define the G3 sequence calculus for quantified C. We have axiomatic sequence now for literals, yes. So if P is an atomic formulas, we have P gamma arrow P and not P gamma arrow not P. So we build in monotonicity or weakening here. We do not just have P arrow P and not P arrow not P, but we need the two axiomatic sequence because we are in this FDE-based framework. Then on this slide, we have the sequence rules for the G3 sequence rules for positive intersynergistic logic. What is interesting here is that we have a repetition of the, in the left rule for implication, a repetition of A implies B. This is for purely technical reasons. This is just for proving the admissibility of construction. Then we have some obvious sequence rules for the quantifiers with the standard restrictions, standard variable restrictions. We have rules that give us the double negation laws we have rules for negated disjunctions and conjunctions that give us all the De Morgan laws. We have sequent rules that make sure that not A implies B is interderivable with A implies not B. And we have sequent rules for negated quantified formulas that make sure that the universal and the existential quantifier are interdefinable by means of strong negation. And then we add either this rule, GEM, which is the law of excluded middle rule for arbitrary formulas, or we add only the law of excluded middle rule GEM-AT for atomic formulas. And then we can easily show that for any formula A, we can prove A gamma arrow A. And the versions of the sequent rules where we have some repetitions, they are all admissible. So these repetitions are there only for technical purpose. We can show in this quite standard way that weakening and contraction are height preserving admissible. And we can prove that the cut rule is admissible. Good. So it is admissible also in the presence of the atomic law of excluded middle rule. Good. I will skip this. Then the two proof systems, the axiom system and the sequent calculus, the G3 sequent calculus for C3, for quantified C3 are equivalent. The disjunction property and the existence property, the disjunction property and the constructible falsity property for the addition of the atomic law of excluded middle rule obviously fail. Yes, both P or not P and not P and not P are derivable, but the system is cut free and we cannot derive sequent arrow P and sequent arrow not P, of course. The excluded middle rule is admissible in this system where we add only the excluded middle rule for atoms for quantifier free formulas, not for the entire language. And now we come to the interesting final result. So we can prove that there is an XA. If we can prove it, if we can prove this sequent in our sequent system where we add the law of excluded middle rule for atomic formulas, then A with T for X is derivable for some term T. So this is the existence property and we have its dual. And if you want, I could go through the proof, but maybe I'm already running out of time. I didn't pay attention to the time. So I can also skip this. We can remark that it is known from work by Nobuyuki Suzuki that the disjunction property and the existence property can come apart in intermediate predicate logics. In particular, that in general, the existence property does not imply the disjunction property. So the paper says 2015, it has not yet appeared. It will appear in the outstanding contributions to logic volume for Hiroakira Ono. And the long delay is not due to the author, it's not due to Nobuyuki. Now, the logic quantified C3 with atomic law of excluded middle is an example of a naturally arising and independently motivated logic for which the disjunction property fails, where the existence property holds. So the examples in Nobuyuki Suzuki's work, they are sort of constructed. I can finally summarize. So what did we do in this paper? So we introduced an extension of the connexive logic C with three questions in mind as our motivations. Can we improve on John Cantrell's logic CN? How much of the desiderata listed in this paper I referred to several times can be met by the approach to connexivity by tweaking the falsity conditions? What is the relationship between constructivity and the law of excluded middle? So here are our answers. Cantrell's classical conditional can be replaced by a constructive one. This is interesting. C3 is a totally connexive logic with respect to the strong implication if we think of negative satisfiability. And finally, the law of excluded middle does not necessarily exclude properties that are usually regarded as indicating constructivity. So we have, if we add the law of excluded middle, for atoms, we nevertheless may have the existence property and its dual, although we do not have the disjunction property. and its view. And as always, if you have some observations, you come up with new questions. So here are additional questions. Can we take other conditionals than the constructive conditional? Can we replace the classical conditional in Cn by a weaker one, by another one? Which system is minimal among the family of totally connexive logics? And are there interesting variants of the disjunction property and existence property that hold in QC3 or related systems, as they are discussed in another paper by Nobuyuki Suzuki? There's another slide on the connexive Lambeck calculus, but I think I better stop here. Thank you very much for your attention.
Thank you very much, Heinrich.